electricity. We have here different problems. We have one here, another one there, another one there, another one there. Okay, so let's start up. Number one, if you can follow it like this, you have the battery, you can follow it just one flow. This is series, so this is series. The same thing, we have a switch there, some lamps, but we don't have any deviation, so of course this is a series. On this one, we start on the battery always, and we have two ways here, and then we continue here. Oh, another. So in this one, in that one on the bottom, we have a different one. This is a parallel. Let's see this one. We have here. Again, we encounter this deviation, so we have another deviation here, etc. So this is parallel diagrams. So let's see our parallel circuits. Okay. On this one that we have here, we start from the battery, and we have a deviation, so this must be parallel. And this one, we go in just a circle, so no deviation. This is a series. Very easy. Let's go to the next one. Okay, in this one, that problem that we have here, this one on my side, this problem, they are asking us what would be the voltage in V1, V2, and V3 if if VT, or the total, or the battery we have here in the battery, is 3 volts. So we have here 3 volts, and then it says what would be the current in A2, meaning here A3 and A4, if we have 0.5 amperes here, 0.5. Okay, so what will happen here? So we said that the voltage, remember the Christmas series, we have a very low voltage because we have many resistance. So in series, we get and we divide the voltage in the amount. So we have 1 volt here, 1 volt here, and another volt here. And the mass of the, like, remember the analogy that we have, like the mass of this or the electrons, the amount of electrons, they go, and basically they don't change. So we have 0.5 in here, we have 0.5 in here, on all of this we have 0.5 all around. Now let's go to the next one to see what happens in parallel. Here in parallel, we have a battery that's 12 volts. But we said that in series we have the same, but in parallel we have, well, I mean, as the opposite. In series we have the voltage drops. Here we have the same voltage, so we have 12, 12, 12, the same voltage in parallel, because this is a parallel circuit. And then they say we have 2 amperes here, so it happens the opposite. Now the current is going to be divided here, so we have 1, 2, 3. In this case, we will have here another 2 because they will be together, but here we will have just a little bit, 0.66666, yes, on all of them, 0.666, which at the end, if you add them up, you will end up with the 2, right, with the 2 amps, amps at the end. Remember, current is in amps, voltage or volts are voltage is in volts. Let's go to the next one. Okay, a component of 8 ohms, so we have a resistance, has 2 amps flowing through it. So we have resistance and we have current, and what they want is the voltage. So basically we know VIR, remember the Ohm's law, and we have basically the current, we have 2 amps, and then we have 8 ohms here, there, well, 8 ohms, and we have 16 volts, 2 times 8, 16, so there you go. And here on this other problem, we have resistance, 16 ohms, and the volts, but they are asking for current. So basically, from here, from the current, we solve for I, or the current, and it's going to be the voltage over R, over resistance. So it's 12 volts over 6 ohms, and it's going to be 2 amps. So that will be the current. On this one, we have 48 volts, so we have voltage, and we have 4 amps. They want the resistance. We solve for resistance, and we have the volts over the current, and we will have 48 volts over 4 amps. We will get, as a result, 12 ohms. Now, this is work, energy, and power. This is a different kind of problem, different. So in this case, we're going to use the formula. We said that there's a man that pushes a refrigerator 12 meters. So we know that work equals force distance. So we're going to multiply the force that we have, the force times the distance. We will get 1200 newtons meters, or in other words, in other units, or this, the complete unit will be joules, which is newtons meters. Or in this case, because we have 1200 or 1200 joules, it will be 1.2 kilojoules. Okay, so there you go. Let's go to the next. And this one, they're asking for power. And remember, power is how fast you can do work. So work divided by time. So we already know that on the previous problem on 2.6.1, we have 1200 joules divided by time, right? So we have the time here. And that will be it. We divide those and we will end up with a power of 13. Let me read it. Yes. 134.83 watts. Yes, that's what it says there, right? Okay, let's go to the next. Okay, remember in this problem, what we need to do is we need to get the component in X, because X is where it moves, right, in the horizontal direction. So that's why we need to take this component. What we do in here is we take this X, and you know, we have a triangle here. So 30 degrees, and to take the S, we use the cosine. So Fx is F, cosine of the angle. We calculate it, so it's 140 cosine of 30, and it's this is 121.24 newtons. That will be the force, the force in X, right? Now, if we want to know work, we already have that it's that is force. We take the component, we use this one, and it moved 15 meters. So 15 meters times the force. So we already have the force here, the 15 meters. We multiply them, and we will get a work of 1,818.6 joules. Now let's go to the next problem. And this one, they ask us what will that work, the work that we just calculated here, what will be the power? So remember, power is work over time. So we divide it by time, and we end up with this, 288.67 watts. Here we have, what would the potential energy? This is a different, this is about not only work, but energy. We already talked about power, right? So what would be the potential energy reference to the ground of, we'll have a bird here, and we have a height of 28 meters. And here we have the ground, right? There you go, 28 meters. And If you remember, the equation is potential energy is equals to the mass of the object, and the gravity, and the height. So the potential energy is just the mass, 9.81, which is gravity, and 28 meters, which is the height. We multiply those and we get this result. For this problem 6.6, what would be the potential energy of this desk? That is a 25 kilogram desk that is in CETEC. CETEC is in the 3rd floor. So, well, it's in the 3rd floor. And so in reference to the 3rd floor, which is a 16 meters height, what would be the potential energy? And the answer is 0, because imagine we have a building. In that building, we have the 3rd floor here. And it doesn't matter where it is, but if you take the reference of this desk here with reference to this floor is 0, because if you remember, the formula is the potential energy. Let me see if I can get away with this. Potential energy is equal to what? M, the mass, G, gravity, and H. But what is H? H, in reference to this, is 0. Of course, it has a height from the ground, but really this will be 0. So the potential energy will be 0. So this is the end of this review. Remember, I did not went into great detail because we already saw this in class. And this is not a class, it's just how to do the problems, how to solve them, so you can study for your final test. So I hope that this was useful for you, and I'll see you then. Have a great study time, and see you later. Keep studying and keep it real. Bye-bye.